So I'm going to be talking about probabilistic programming languages. This is the applications week, right? So far, you haven't been learning about applications, apparently. I don't know if that's true. But we're going to be learning about probabilistic programming languages, which I think are a very interesting application of programming languages. And I kind of wanted to spend the first 15 minutes of this lecture or so giving you two perspectives on why I think you should care about probabilistic programming languages, right? I'm going to try to give you an argument for why this is something that you should be interested in. Because I think for a lot of you, you probably haven't seen probabilistic programming language before, and maybe even the word probabilistic is a little bit intimidating, right? So I kind of wanted to just give you some perspective I have on why I think this is an interesting thing, right? So I think there's two, any sufficiently interesting and important topic has two very different groups of people that want to learn about it, right? And I think that with probabilistic programming languages, by the way, I'm going to call those PPLs a lot. Sometimes peoples, if you want to be clever, right? So there's two very different groups of people that care about these things, right? The programming languages people and the AI people. I'm sorry, we're going to talk a little bit about AI. Don't worry, just a little bit, Trust me, it's interesting, right? So that's the PL perspective on probabilistic programming languages, right? Let's start with that one. That's the one you're probably more excited about, right? So the PL perspective on probabilistic programming languages kind of stems from the following argument, right? So there's an argument here. So the PL argument for why you should care about probabilistic programming languages. All right, first premise, one, you want to verify things. You want to verify programs, right? We all heard that Dijkstra quote, right? Like verify, not test, right? We want to be able to give a formal meaning to our programs so that then we can verify mathematically that they satisfy some specification, right? This was like an old idea in programming languages, a very important one, right? Premise two is that programs have uncertainty in them. Programs have uncertainty in them, right? So what does that mean? It means that some programs have some probability of doing one thing or another thing, right? And this comes up in a lot of contexts. It comes up in randomized algorithms. These are algorithms whose correctness depends crucially on the ability to do something random, right? Primality testing is a classic example, but there's lots of very interesting and very useful randomized algorithms. Another one is distributed systems and networking. Randomization is often crucial for things like tie breaking and leader selection that require breaking, some sort of determinism in the system in order to select a unique element, right? And it comes up a lot in distributed systems and networking, right? And let me see. I think I might have even had another one that I wanted to mention, but it's not important. I think that there's so many ways that, that programs can become random. Yes, differential privacy is a really cool example. Differential privacy. These are programs that use randomization in order to give you some notion of privacy, not leak data about individuals, right? And you might even see later on in some of the other lectures during this week, in cryptography and in security, there you may see echoes of probabilistic reasoning there as well, which provide information theoretic guarantees about various things for crypto systems and things like that, right? So programs have uncertainty in them, and it's an important part of their meaning, right? And so from this, you can conclude that programs should have probabilistic semantics. Programs should have probabilistic semantics. What does that mean? It means that our programs should have baked into them some underlying mathematical meaning, some underlying probabilistic uncertainty, so that we can represent these kinds of interesting randomized algorithms, these kinds of interesting differential privacy, distributed systems. So as a consequence, we've been exploring probabilistic program semantics within the programming languages community for quite a while. The first paper was a paper from Dexter Kozin. Second time Dexter Kozin has been mentioned this week, very important guy. And that paper was, I believe, from 1982. which introduced the term probabilistic programming, right? And this is a very interesting paper. It has a lot of interesting perspective. At the time, he was very interested in studying it from like a theoretical computing standpoint, when we were very interested in randomized versus deterministic models of computation. If you like that stuff, it's a very interesting paper. So, since 1982, this has been a very thoroughly studied sub-area within programming languages, and at every single major programming language conference, you'll see a few probabilistic programming semantics papers. Okay. So I think that the argument for why you should care about probability from a programming languages standpoint is actually pretty ironclad. And I wanted to show you a different perspective on why you should care about probabilistic programming, which maybe isn't so obvious to you, which is the AI perspective, which I think is very interesting. So why probabilistic programming languages from an AI perspective? Why probabilistic programming languages from an AI perspective? So what's the goal in the AI world? There's many goals. But I think one very good goal is we want to be able to create agents that reason rationally about the world. We want to create agents that reason rationally about the world. If you go and look at old AI motivation, this is kind of what it all looks like, right? We wanted to have chess-playing robots. We wanted to have robots that can talk to you. But really, it's about this reasoning rationally about the world, I think, that creates a lot of the useful tools from within AI. And from these things, lots of little other motivations have kind of sprung out, right? So we want to create agents that reason rationally about the world. And then the problem with that is that the world, in order to do this, then, what do we need? We need a way of representing the world to the computer. We need a way to represent the world to the computer. How can the computer reason rationally about the world if you can't represent the world to the computer? And this brings us to a really important picture, which is this modeling paradigm. And the modeling paradigm looks like this. You kind of have an abstract picture of the world. Here's my world, right? And then I need to somehow encode this thing into something that like a computer can understand. Check out my computer. Yeah, thank you, thank you. And then you have to do what's called reasoning to get some action. Very high-level picture. But you can cook up a lot of ways in which this is a very typical workflow within the AI world and also within lots of other contexts, right? And it's this step here that's really interesting, right? That's a really interesting step. How do we take something that's really complicated like the world and write it down in a way that the computer can understand? Well, that sounds a lot like programming, right? It sounds a lot like programming. We're almost there. There's another step. There's another step, which is that the world is too complicated. The world is too complicated, right? There was a time when people thought we'd be able to write good enough models to where we'd just be able to write down deterministic programs in logic, right? And this was like the old logic program in AI. You can go read old stuff by John McCarthy and people like him about how we were going to write down large logical deductive systems, often in first-order logic, that would tell me everything I needed to know about the world in order to be a rational agent. Now, that didn't really pan out. But a lot of those efforts led to things we like theorem provers and stat solvers and cool stuff. This program of trying to take the world and write it down as some deterministic system of logic and rules didn't really pan out. What happened? Well, this problem, right? The world is too complicated, right? And kind of, I think, a really important next step in this chain of argument is that we need probabilities to simplify the world. And I think this was a really big insight in the mid-1980s. And in particular, there's someone named Yuta Perl, who I think was extremely influential. He's a Turing Award winner in making this argument to the broader AI community, that we needed to transition from logical to probabilistic systems of reasoning about the world. And at the time, this was highly controversial. He had to create his own conference called Uncertainty in Artificial Intelligence because they wouldn't accept his papers at the AAAI conference because they were too probabilistic, right? So it was a big ideological clash in the 1980s that Yuta Perl completely and unequivocally won. I'll go on recording saying that. Pretty much all of the AI models today have probabilistic reasoning under the hood. And nowadays, AAAI will happily publish your probabilistic reasoning papers, right? But you know, what was his big idea? Well, his big idea was to propose what I would consider to be a probabilistic programming language. He called them probabilistic graphical models. And what these were they were a simple graph. In his case, they were directed graphs that described the relationship between random quantities. I'm not going to go into probabilistic graphical models. You could have an interesting class. Lots of universities have courses you can take on probabilistic graphical models. But from this perspective, you can think of these as a small language that tells you something about the world, in particular the relationship between unknown and random quantities, right? And I think that this insight about being able to give a language whose semantics is probabilistic in order to describe a complicated world and reason about it is very strong and interesting motivation, right? And it begs the question, and this is kind of a motivation that I find very exciting, is, well, graphs are so boring, right? And it's not really how the world works. The world has interesting structure. The world has loops and recursion and all sorts of stuff, right? And then kind of the motivation for probabilistic programming from this perspective is PTLs provide expressive languages for modeling the world. Right? And I think that's very compelling motivation, and it kind of stems from this kind of reasoning here, right? And so whenever there's two communities that are very interested in the same topic, well, there's always kind of a parallel development between the two communities where they're kind of each developing in their own independent methods and independent kind of approaches and problems and so on to the challenge of developing this same kind of technology. And I think kind of one of my goals from this class is to take some of the stuff from this world, which you don't know enough about, I think, and show you why you should care about it as like a programming languages person, right? So that kind of brings me into kind of what this class is and what I'm trying to do. Let me see. Okay. So the goal of this class. I want to show you how to make a probabilistic programming language from scratch all the way up to being pretty good, right? And pretty good means that it runs reasonably well. You can actually solve some of these things with it, right? So we're going to talk about some of the actual low-level things you need in order to implement one of these languages. So the goal of this class is really to implement a series of languages. Probabilistic languages. Along the way, we'll learn about what they are and how they work. So on the Slack, I uploaded a GitHub link, which has some code in it, which is some of the languages that we're going to talk about in the class. And you can actually go in there and play with them. They're all like single file OCaml languages. And some of them I've left blank with starter code in there for you to try to implement before you look at the solution, right? And I think that that's actually a really useful way to kind of learn this stuff. And I would suggest you do that. So there's going to be kind of, here's the outline of the class. I'm going to talk today about the syntax and semantics of probabilistic programming languages. Tomorrow I'm going to talk about sampling. And you can think of these, if you like semantics, as denotation and operational semantics, right? And then I'm going to talk about tractability and expressivity. And you can think of this like language design, right? So this is like denotation, meaning of programs. This is like operational semantics, how we actually run them on our computer. This is like language design, which is like what are the implications of different features we put into our languages and how do they affect these two, right? And then the fourth day is kind of going to be, I think we may need some slack on that day. But if we have time, I'll talk about kind of topics, more advanced things within these categories. That's my plan. We'll see if we can stick to it. Okay. Are there any questions so far? I feel like I've delivered propaganda, and some people are like, no, I disagree. Yeah?
So can you explain the intuition of how probabilistic reasoning simplifies like the reasoning in AI?
Yeah, great question. Yeah, the question is, how does probabilistic reasoning solve this problem? Right? That's a big question. It's hard for me to answer that in 3 minutes. So Yuta Pearl has a book, which is called Modeling. It's called Networks of Plausible Inference, Networks of Plausible Systems, something like this. Let me see if I have it in my slides here. I can't find it. OK, Networks of Plausible Reasoning. Plausible inference. Thank you, member of the audience. This is a real classic, and it's totally out of print. So you'll have to use your detective skills to find a PDF. I'm sure you can manage. Yeah, I mean, if it was in print, I'd buy it. So this book starts with like a 1-chapter argument for why probability is the answer to the question of, why not logic. And it's beautiful. It's such a good chapter. It's really interesting. But kind of, there's 2 punchlines, I think, that are really interesting and important. One is that logic is monotonic, right? So imagine I have a big database of facts and logic, and I'm adding more and more facts to that database. Think of them as adding conjunctions. The set of possible worlds gets smaller and smaller and smaller. But the problem is that the real world is often not monotonic. Sometimes we need to forget things that we've learned in the past. And a lot of these systems, in particular, I'll tell you one, which is called Psych, which is a really fun thing. If you Google Psych, you'll find a lot of fun things about it, was that they had to have very complicated systems for forgetting facts that were no longer true. And it ended up causing some really big problems. This is how we got things like fuzzy logic, blah, blah, blah. It gets very, very complicated. Right? And Yuta Pearl came along and said, guys, that's all just Bayesian inference. If you just have probabilities, then we can actually unlearn things in a principled manner by doing Bayesian updating. And we'll talk a little bit today about Bayesian updating and why that solves the monotonicity problem within logic. But I think that's a very compelling argument for why logic is insufficient. Right? We just have, so that's one reason. Another reason is that probability simplifies. Right? It's like, if I zoom in enough on the world, perhaps it becomes deterministic. Right? But obviously, that's not how it works. Like us as humans don't model the entire world and all of its possible interactions. We use heuristics. Right? We use simplifications. And from that perspective, there's an empirical argument that probability is a very good simplification, right? It's hard to make an epistemological argument about that, but there's an empirical argument that that's a good way of simplifying the world. So that's an interesting question. And if you want to have like a really long read about it, check out this book, which has a really nice argument, which I think is very interesting. Any other questions? Great. OK, let's get into it. Let me work over here. What are probabilistic programs? What are probabilistic programs, right? We've been talking a lot about what they are, and maybe you have an idea in your mind. But probabilistic programs, in short, are programs, a little bit circular, forgive me, that denote probability distributions. Programs that denote probability distributions, right? So let's see an example of one. Let's see an example of one. So I'm going to use the following syntax. We'll say X gets flip 1/2. If you like Haskell, this is like monadic bind. We're not going to talk about monads, though I think another Steve will give you lots to know about monads. But I will give you this. And we'll give you the semantics, so don't worry. Flip 1/2. Okay. Then we'll say return X or Y. Okay? That's my program, right? That's my program. So what is it doing? It's saying, well, X is a random variable. It's a random quantity. And it comes from a coin flip, which is true with probability 1/2, right? This syntax means true with probability, and then false with probability 1/2 as well, right? So what does this do? Well, it flips 2 coins, and it returns true if either of them is true. All right, that seems easy enough. So what does this program denote? Well, you know, if you've ever programmed with a programming language with a random number generator before, you might think, well, you know, these are just calls to a random number generator. These just give me true and false, and then I get one run through my program, right? Maybe this is outputting true or false. Now, the key thing about probabilistic programming languages is that we actually give their semantics, and we'll write it this way. It's actually going to be a probability distribution on values, right? It's going to be a probability distribution on values, and it's the probability that this program returns true. Who can tell me what that is? What's the probability that this program returns true? Yeah. 3/4. 3/4, yeah, very good. 3/4, right? So it's actually going to be a function. It's outputting a function. And we're going to say this guy here is semantic true, right? And that gets mapped to a number, which is 3/4, right? And then semantic false is the other possible value, and that gets mapped to 1/4. Okay? So our programs are going to be outputting these like functions here that tell us the probability of various values. Right? That's the meaning of this program. Right? So just to give you a little bit more formalism here, we'll say a probability. So we're going to say a sample space it's just a set. And for now, we're just going to think about countably large sample spaces. I don't want to talk about sample spaces that are too big. And in this case, it's equal to the 2 possibilities we got from this program, true and false. Is there a question? Yeah.
Is there a reason why we use TT and SF and not?
Purely syntax. I'm going to be very careful about distinguishing semantic from syntactic true. Right? So there's going to be a syntactic true in the program, which is true in text. And then I wanted to have a semantic, which is TT. Right? And it's like, oh, why don't you use top and bot? Well, bot's going to mean something else.
We have true beside the arrow. So true with probability 1/2.
This says flip.
On the right column.
Yes, this says true with probability 1/2. That's the meaning of flip. Yeah, yes, very precise. TT with probability 1/2. Yeah, there you go. There you go. Yeah. Yeah, question.
Actually, now is true is syntactically true and TT is
Semantically true.
truly true? Then isn't that, I mean, I guess it's in the item. It returns true, like literally in the program, it returns the symbol true. Probability.
I'm not sure how to parse that. I think that if you guys want, I'll just put true everywhere. I think it's kind of it's a matter of being, I guess, hygienic, right? So, later on, I'm going to tell you that the meaning of this symbol true, this syntax, is going to be a function which maps values to probabilities, right? It's not going to map syntax to probabilities. And the language of our values or our semantic domain is going to consist of these symbols here, just to distinguish them from that. But it's kind of a pedantic game. I don't think if it's confusing to you, it's fine. You'll do the right thing on accident. Right? Okay. So we're going to say that's a set with these two elements, right? And then we're going to say a probability distribution on omega is going to be a map from omega to the interval that sums to 1. Okay? So this is just sums to 1. So such that my board hygiene here was poor. Let's do this. Such that sum over all little omega in big omega, probability of little omega, is equal to 1. This might differ slightly from a definition of a probability distribution and probability space that you've seen if you've taken a measure theory class. I've specialized it to the countable case. Don't think too hard about it. Okay. So how many of you guys have seen these semantic brackets before? I'm curious. What have people seen? Have we talked about it in this OPLSS yet? Who talked about it? Everyone. Great. Okay. Good. So yeah, semantic bracket. It's a very misunderstood guy. It's very confusing, I think. But we're going to give a semantics to probabilistic programs, these little probabilistic programs, that associates that syntax with these semantic domains. Right? So if you've heard of semantics, it's like, well, it's a way of taking my syntax and associating it with a quote-unquote mathematical object of dubious origin that tells me everything I need to know about that program, right? In the sense that it captures the structure of that program, also its contents, right? Very tricky. So in our little probabilistic programming language, we're going to associate programs with these probability spaces, these probability distributions, right? Now I'll pause and say the semantics of probabilistic programming languages, meaning the possible meanings you can assign to this semantic bracket, is very much an open research question. It's very, very, very difficult to get a good semantic domain for very rich languages. And that's another thing I kind of wanted to bring up in the course, and kind of as we go through this course, is like, what are the interesting research challenges that people are thinking about right now? Right? So Amal briefly mentioned in one of her lectures, the reason why we like logical relations is that they let us say things about programs without descending into the madness that is the semantic bracket. Right? It lets you say things like these two programs are equal without ever constructing a mathematical denotation of those two programs, which is great because that's really hard. Right? Like even just for this untyped lambda calculus, it took a long time to come up with a good denotational model. As soon as we throw probabilities into the mix, it's really crazy complicated. Right? It's also very interesting, very complicated. We're not going to talk too much about that, but I can give you some references if you're interested in learning more about that. So for now, we're going to focus on very, very simple syntax, very, very simple semantic domain. And that's going to make it so that we can give a nice compositional semantics to a small programming language. Okay? Any questions? Any questions? Good. Okay. Let me see. Let me move over here. Syntax. Okay, so this language is called tiny people. Syntax of tiny people. So if you go into the GitHub repo that I gave you, you'll see a tiny people folder with an implementation of tiny people for you to play with. So its syntax is as follows. It's going to have pure expressions, which are expressions that don't have effects, right? So no probabilities. And you can put a lot of stuff here, right? We're going to have identifiers. We're going to have if. We're going to have, what else do you guys want? We can do conjunction. Let's start with that. Oh, and then let's have our base cases, true and false. Syntactic true and syntactic false. Okay. Now I can write programs other than identifiers. Okay? So this is my pure terms. You can put anything you want here, really, as long as you can give it a denotation. And then we're going to have our effectful terms, or our probabilistic terms. And these are going to be where we put all the business, right? These are the ones that are going to have the probabilities going on. Now, if you're familiar with monads, you might be thinking, why are you doing a syntactic separation? You could be using a type system. I'm keeping it simple. Okay? We're just going to have a purely syntactic separation. If you wanted to, you can use your monadic type system and separate them that way. Right? So let's see what we have here. So you've already seen our friend the bind. Right? So this is going to take some probabilistic quantity, bind its value to x, and then execute e. It's going to be its meaning. Right? And then we need a way of getting pure things into the impure setting. Right? So that's going to be return. Not to be confused with return from your favorite imperative language. Right? This takes a pure thing and makes it an impure thing. Okay? And then we need a way of introducing randomness. Right? We've already seen that. It's going to be flip. Okay? So it'll be like this. Let's say flip theta. And then
Why not just let theta be that expression?
Because then I wouldn't have a way of introducing it. Right? Because I'm only allowed, oh, this was supposed to be p. Or wait, no. Yeah, then I can do that. Yeah. I confused myself. I actually had in my notes flip theta, and then I fixed it on the fly, and then I got it wrong. Thank you. Right? Okay. So now this program over here, hopefully, is a syntactic program I can write in that language over there. Correct me if I'm wrong. I think I'm good, right? Yeah, this is going to be a real. So I'll permit you to have a fraction there if you want. Any other questions? Yeah.
You don't have disjunction for the fourth.
Yeah, let's add disjunction. You could do it with if, right? But let's make our lives easier. Yeah.
Can you assign a return to a variable? So can I get x gets return?
Yeah, that's okay. Yeah, that's fine. Yeah. Oh, the question was, can I put, is this a valid program? Return true. And then maybe return x. Is this a valid program? X gets return true, return x. That is a valid program. Right? And what it's going to mean intuitively is you're going to take this guy, which is a pure program, you're going to lift it into being a probabilistic term. Right? And it's going to be the obvious way to do that. You're going to assign a probability 1 of true. Right? And then I'll bind it to x. It'll just make x be essentially a deterministic quantity in the context of the sub-expression. And then you can evaluate the sub-expression. We'll get there once we start talking about the semantics. Yeah, question.
Do we get a sequential composition outside of the bind? Is there like other?
No, we're going to keep it all to the bind.
Okay.
You can grow the language. Right? If you want to, make it bigger. It's going to be easy to make it bigger. But to make our semantics very simple, I'm going to give you this tiny language here, and we're going to give it the semantics. Yeah?
What about the double bar operator syntax?
Say it again?
The double bar syntax. Like x double bar y.
This is or. Did I use a different syntax? Yeah, let's use this one then. Sorry about that. Yeah, we'll use our friend logical or notation. Yeah.
If I'm to think of this with a type system, is it just a type system with just Boolean and a monad and Boolean?
Correct. Yeah. 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 Okay, any other questions? Good, let's give it a semantics. Let's give it a semantics. All right, so we already saw an example of what we wanted our semantics to do. And whenever you're making a semantics, you as, I guess, budding language designers, maybe, you should always make some examples before you make your semantics. And think about what you want them to mean, right? Because until you do that, it's pretty tough to actually write down the mathematical rules of what these terms ought to do, right? So we'll start with a simple enough base case, which is going to be the semantics of the pure terms, right? So let's start with the semantics of the pure terms. Semantics of the pure terms. Now, there's many, many ways you can go about doing this, right? We can use a substitution-oriented way of giving these semantics. We can use an environment-oriented way of giving these semantics, and you've probably seen examples of both. We're going to use an environment-oriented way, but we could, of course, use substitution, right? So what this means is that terms are only going to be given meaning in the context of an environment, right? Which tells you what the free variables are. Because if you look at our syntax, you'll notice our pure terms might have free variables in them, and we need to be able to interpret those free variables, right? There's a lot of ways of doing that. You can treat the free variables as arguments to a function and so on. We're going to do it this way, right? I'm going to define a semantics on the pure terms, right? And what it's going to do is it's going to map environments to Booleans, right? It's going to do the fairly obvious thing where if it encounters X, it'll look it up in the environment, return its value, right? Now, you could, of course, make these environments be well typed and make the semantics only defined on the typing judgment. I'm trying to keep it simple, right? So this will be a partial function. If the environment doesn't have a name in it, it just won't be defined on that, okay? So let's see an example. So if I give you X, and I'm going to write my environments using these square brackets here, and in this environment, we're going to say X gets true, right? Well, then that's just going to equal true, right? It just looks X up in that environment. The rest, I think you can probably work out, right? Conjunction, disjunction, true and false, they're all going to do kind of what you expect, right? So like the semantics of true, syntactic true, of course. And this is going to be true for any environment row. We're going to denote our environment's row, by the way. Well, that's just going to be true no matter what, right? So we can go about giving a nice, simple semantics to all of our pure terms in this way. Okay, question?
What happens if X is assigned fleet at
Ah, we haven't gotten there yet, because you're not going to be able to. You'll see. You'll see. You'll see. You'll see. Hopefully, the pure semantics are nice and easy. All right. Do we need more examples? Are we good? Yeah.
What did the subscript P do?
Pure. All it's saying is these are the pure semantics. Any other questions? Yeah.
If I write to X several times, I just take it to right.
Say it again.
If I write to the variable X multiple times, several values, you just take the rightmost.
Ah, don't worry. We haven't gotten to, you can't even write, you can't update variables yet in the pure language. All the fun is in the impure language. Right? That's where the fun's going to be. Yeah.
Just to check my understanding, so if you have the semantics of X applied to an environment where X maps to FF, then you just get false.
Correct.
Okay.
Correct. Yeah. Yeah. You just look up, anytime you hit an identifier, you look it up in the environment. If you guys want, I can give you the full semantics. It's also going to be in the notes. I'm going to give you some notes. You can read those full semantics there. Yeah.
Are there any other values X could take besides TT and F?
Nope. X is only going to be able to take true and false. So environments, these guys are actually maps from identifiers to Booleans, which I'll denote with this Blackboard B. Yeah.
So are you drawing a distinction between Booleans and our ground set over here?
No. This was kind of an off to the side definition of sample space. Sorry, I lost track of where you were asking the question. But yeah, let's not dig into that too much. Yeah.
Shouldn't that map be mapping to the syntactic true instead of the semantic true?
No, because we want this thing to give us semantic values. Yeah.
If you could repeat that question.
Yeah, so the question is, could we make this environment map from identifiers to semantics? And okay, I need to give you the full rules. Let me show you. Okay, so let's look at an example. So we'll say P and P, P1 and P2 of row. Okay, we want to evaluate that. Right? So what do we want to do? Intuitively, well, you want your semantics to be compositional. You want to define the meaning of big terms in terms of the meaning of small terms. Right? So what I want somehow is to be able to do something like this. Well, I evaluate P1, right? And I'm going to evaluate it on the same environment. And then I'm going to have out here like a semantic conjunction. I know. And then, sorry, my subscripts are all missing. P, P, P. Right? I want to be able to do this. Right? Where I get the semantics of P1, get the semantics of P2, and then conjoin them together. Right? And if you don't like the semantic and, you can do cases. You can be like, if this one is true and that one is true, then semantic true. If that one is false, etc. Right? So in order to do this, I don't want to get a syntactic true out of the meaning of an identifier, because I want it to be a semantic true so I can give a meaning of my semantics in compositional terms over my terms. This is an interesting and important point actually about giving semantics, is you want your semantic domain to be kind of distinct from your syntactic domain. Right? Otherwise, you're left with syntax and your semantics, and then that can be very annoying, actually. Any other questions? Good. Okay. Pure terms are not too bad, hopefully. Now for the probabilistic terms. Okay, so what are their forms? Right? Did I leave my syntax? I did, good. Right, so there's 3 cases we have to handle, so I need to give you a semantics for each case. And I need to tell you the type of the judgment. Right? So we're going to have this semantic form. And we already talked about what it should mean. It's supposed to denote a probability distribution on values. Right? So what is that? Well, we're still going to have some open terms. So we're still going to need our environments floating around. So you're going to give me an environment. And then I'm going to give you a probability distribution on Booleans. Right? So then it's going to give you a probability distribution on Booleans. And if you don't like the binding order, I'll put that in parentheses for you. Okay, and then this guy here, that's going to be a probability distribution. That's the type of our semantics, and I'm just going to leave this one unsubscripted. Okay? So you give me a term, and then you give me an environment, and then I get a probability distribution on values. Yeah.
And that probably the probability distribution is the same probability distribution where all its terms added to 1.
Yeah, it's got all out of if you sum over true and false, you got to get 1. Okay. Otherwise, it's not a probability distribution. Okay. So once I show you a simple case here, I think you'll be comforted because it's really not too bad. Let me do it on this board. That board is running away from me. It's afraid. Okay, I understand. All right, flip. And let's do 1/2. What the heck? Okay, semantics of flip 1/2. Okay. Well, you got to give me an environment. It can be any environment, right? And then, what are you going to get out? What's the probability distribution? Hopefully, it shouldn't be too hard. What do people think? What do I get out? Yeah. What do you? Go ahead. Yeah, you.
Sorry, I don't know if people are here.
Yeah, you're fine.
True is a half, false is a half.
Yeah, there you go. True gets 1/2, and false gets 1/2. True gets a half, and false gets a half. No matter what row is, right? We're just going to ignore row. Maybe you haven't seen this exact way of writing a definition before. This just means you have to give me an argument row, and I'm just going to bind it to row, right? And then I get out this function. And of course, if I wanted to make this an arbitrary real, or whatever, let's call it R. We'll get this gets R, and this gets 1 minus R, and that better be between 0 and 1. Otherwise, take your program somewhere else. Right? Okay. Okay. So flip's not too bad. Let's do return. Return P. What do people think? What do people think? Yeah. Yeah, so you're gonna, it's got to be in terms of that pure expression, right? And there's going to be kind of two cases we got to worry about, right? So you give me an environment row, right? And then it needs to be a function. So I'll give you this syntax for defining a function. So you give me a v, and then I'm going to do something depending on, I'm going to do case analysis, right? I'm going to do some case analysis. So if, when I evaluate P under the pure semantics in the environment row, that gives me back V, what do I do? What's the probability of this? Like, if you give me a V and it's equal to that, what do I return? What do people think?
1.
1, yeah, 1, right? I'm assigning a probability 1 to the instance when you give me a value that matches what P is. Make sense? And then we're going to do 0 otherwise. Okay? Yeah.
Why do these semantics not have a subscript?
This one should. That's purely just a design decision. I wanted to write fewer subscripts. If you wanted to, you could make this one be E to match the E term over there. Sometimes that's nice. Sometimes it's clear from context. You can kind of elide them when it's clear from context. A lot of people do. I just didn't want to do that. Yeah.
What happens if P contains terms that, or like variables, for example, that aren't defined in the environment?
What happens if P contains terms that aren't defined in the environment? Yeah, I hid that. In the beginning, I just said, assume it's a partial function. It's not defined there. Really, if you wanted to be very kosher, you would add a typing context here and say row needs to be well typed according to gamma and types the term and blah, blah, blah. We're keeping it a little loose here, right? We're just going to make it a partial function. But if you wanted to make it a total function, you could make it a semantically guided semantic, a type-directed semantics, add a gamma, etc. Or you can use substitution. Okay? It's a good question. You need to be very careful about that kind of stuff. Any other questions? Okay? All right. Now for the big boy, which is where all the work is, which is bind. If you like monads, by the way, this is in fact the unit for what's called the probability monad. And this is in fact a bind for the probability monad. And if you want a fun exercise in monads, prove that this is a monad. What do people think? What do people think?
Could be conditional probability.
Yeah, we're going to need to do some work here. We're going to need to do some work here. Okay. We want to be able to define the the meaning of this term compositionally. Right? We want to be able to give the meaning of this term in terms of E1 and E2. Right? And, how are we going to go about doing that? So it's good when you're kind of thinking to think about an example. Let's think about a very simple example. Let's keep as much of my syntax as I can. Let's look at a simple case. X gets flip 1/2, and then return X. Okay, so what do we want to have happen here? So we kind of know this thing should be returning 1/2, probably 1/2. So we can use this constraint to kind of figure out what our semantics should be. And this is a very good thing to do, right? You just write down your term, write down the semantics you want, work backwards from there, right? So what should we be doing? So intuitively, what do we want? So we kind of have, this case where if X gets true, then, so let's just see. So we're going to have this guy here, flip 1/2, right? We can kind of know that we need to evaluate the semantics of this subterm. Question?
According to our syntax, aren't we return only pure terms?
Say it again. According to our syntax, where's the...
Only return pure terms.
Yeah, X is going to be pure. X is going to be pure, right? We can only get identifiers in the pure context. So how do we fix that? How do we make X be pure? We're going to have to do case analysis, essentially, on X, right? We're going to have to make it true or make it false, right? So there's going to be two cases, right? If this guy is true, right, let's just say there's an environment row. So if this guy gets true, then I'm going to evaluate return X in a context where I make X be true. Right? We're doing case analysis. All I'm doing is, checking the probability that this guy evaluates to true. And if it does, then I'll just evaluate this guy in the context where X is true. Right? And I'm multiplying by these probabilities and adding these probabilities. Right? And then there's going to be another case, of course, when X is false. Oh, sorry, I'm being sloppy. Semantic true. I made a big deal about it, and then I messed it up. Return X, or I make X. And then I ran out of room here. I'm sorry. This is supposed to be evaluated on something. It gets evaluated on, let's say B. This gets evaluated on B. And then row with evaluated on B, the same B. And then this needs to be X gets false, and then evaluated on B. Sorry about the poor board work here. Hopefully that makes sense. Right? But we can check that that's actually doing what we want it to do by seeing if we get the number we want in the end. Right? So the number we're expecting to get is 1/2. And you can see that because of the way that return works, this will return 0 if X is equal to true and false if 1 if X is equal to true and so on. Right? So hopefully this is suggesting a general form, which I'll write now. Now that we've kind of thought about an example a little bit, which looks like this. So I'm going to sum over V in my semantic domain. Sum over the set of what I'm going to call intermediate values. Right? And then what I'll do is I'll compute the probability that E1 evaluates to B. And then I'll multiply that by the probability that E2 evaluates to, this is all supposed to be an environment row. Row times probability that E2 in row with X gets this intermediate value, that gets evaluated in the context of B prime. Okay, does that make sense? So what I'm doing is I'm computing the probability that the first term steps to some value V. And then I evaluate the second term where I just substitute in X for that V. I make X be deterministic. Right? So now X is true or false. So hopefully this addresses a lot of your questions about how can X be true or false. Well, this is how you do it. All right, so this is called the monadic semantics. It's a good idea to work through this definition. I'm going to give you notes where you can read this in maybe a better way than what my board handwriting is giving you. Questions?
For that second V, is that actually V prime or?
Yeah, so this is V prime here. So I need to compute the probability that E2 in the context of rho with X getting my intermediate V becomes V prime, right? And that's going to be the thing you actually want to compute the probability of, right? So the monadic semantics of probabilistic programming languages, right? There's a classic, really nice paper, I think, from Ramsey and Pfeffer, which really makes a nice, clean explanation of this idea in O2. And there's a classic paper from Michel Guiri, 1986, categorical semantics. Of probability distributions. I believe that's the title. Which works out a lot of the theory of this particular monad and extends it to a pretty ridiculously complicated set of terms, actually. So this is a very cool paper. So if you like monads and you think this is cool, these two papers will pique your interest. Question?
Yeah, so by the fact of using a multiplication, it seems like it's implying that the evaluation of E1 and E2 are probabilistic in the independent.
Correct. Correct.
Like, what is the intuition behind that?
Yeah, that's a great question. There's a bunch of different ways of getting an understanding on it, right? So let me see the time. So I go until 10:20, right? I have 20 minutes? Yeah. Okay, great. So the question was, the fact that a product is happening here somehow implies something about probabilistic independence, right? And the idea is that if I have two independent events, like I'm flipping two coins, and I want to compute the probability that they both land on heads, well, I can do that by independently taking the product that each coin lands on heads, right? This is the notion of statistical independence. And the fact that I'm using a product here to combine this semantics somehow tells me, as was noted, that this is like somehow exploiting that independence. I didn't want to get too into that, though that is a very interesting observation. It is exactly what's happening. We are exactly using independence to construct this probability distribution. And it comes from the fact that the only way of introducing random variables into our language comes from this, which guarantees that every time I introduce a new random quantity, it's independent, right? And then there's going to be conditional independence, which is that once I fix x in the subterm, it will be independent of this one. So it's actually kind of intricate what's going on there. But working out the actual meaning of this, if you like this kind of stuff, is actually quite interesting. You can work out a whole picture of this, where this E1, this E2 is actually a conditional, its semantics is a conditional probability distribution given E1, and then this becomes the law of total probability. You can work it all out that way if you know what that means, and it's quite interesting. Yeah?
So I know that in other domains, these sort of sum of product computations end up being really difficult to compute.
Oh, lovely.
So I'm wondering, like, is it the case that for large programs, computing the semantics is tractable?
You're ahead of me. You're ahead of me. Yeah, the question is, well, this is a sum of products, which looks super intractable, right? How do I actually make a programming language whose denotation is given as a sum of products? And that was something that I wanted to talk about. In fact, maybe I'll talk about it now. That's a great segue. If there's no more questions on the semantics, I think these are best digested in solitude. Take a minute, think about that sum, right? You'll get it. Just work through some examples. Okay. Okay. So I got a really fun question. I don't even know. Did I release my notes? Did you look? That's amazing. I'm not accusing you. Okay. Tractability. Tractability. Okay. So it was just observed that this sum of products looks really scary, right? How do we know that we're going to be able to evaluate these semantics? I'm going to show you that evaluating the semantics of tiny people is really hard, which is very unfortunate. How hard do people think it is? Which complexity class do you think the question of evaluating the semantics of this language falls into? Yeah. Exponential in the number of variables. Well, that's an open conjecture. Probably. Can we be more precise? Do people have an intuition? What do you think? Well, I've told you already. Someone else. What do people think? Do people know your complexity classes? Guess. NP hard, NP complete. What do people think? Yeah. Yeah, go ahead. Sharp P hard, yeah. Someone knows their complexity classes. Yeah, it's going to be what's called Sharp P hard. Okay, so what is Sharp P hard? It's the class of counting problems for counting the number of solutions to an arbitrary Boolean formula. Input is going to be a Boolean formula and we'll call it phi. Then the output is going to be the number of solutions to phi, meaning the number of models that satisfy it. Right? So like a classic example is like if I have x or y, then when I'm going to call sharp sat of x or y, well, that's going to equal, you know, the number of models, which is x equals true, y equals true, and then both are true. Right? So then that's 3. Right? And this problem called sharp sat is the canonical Sharp P complete problem. Right? It belongs to the class Sharp P. What do we know about Sharp P? I'll summarize it this way. Sharp P equals very sad. Very sad, right? Because that is a really hard complexity class, right? It's like counting the number of solutions to a Boolean formula. That's pretty scary, right? Like that's got to be at least as hard as sad, right? Question.
Roughly, where does this sit in like the hierarchy of complexity?
Sure. If you like complexity, look up Toda's theorem, which relates the Sharp P complexity class to the polytime hierarchy. It's actually at the very top of the poly. It contains the entire polytime hierarchy. Oops. Very bad. I can use it for solving quantified Boolean formula, everything. Right? So it turns out that I accidentally made a very intractable language. You thought I was showing you a simple language, but it's actually incredibly hard. Incredibly hard, right? There is a very, very, very simple reduction from tiny people to sharp sat. Very simple reduction from tiny people semantics to sharp sat, right? What is it? So reduction. The reduction is this. You give me a formula of R phi. Let's make it x or y and y or z. I don't know. You give me a formula. And I'm going to give you a tiny people program whose semantics tell me the number of solutions to that formula. Right? How do I do that? Well, it's quite easy. Does anyone have a guess of a program whose semantics computes the count of that formula? Or gives me something that lets me compute that? Yeah.
So for each variable in the formula, you would do a flip of 1/2 and assign each one to a flip of 1/2.
Yeah.
And then return the formula using, you know, your conjunctions and disjunctions and such.
Yeah, and then I just return phi, right? Quite simple. X or y and y. So I flip a coin, flip a fair coin for each variable, and then I just return the formula. And then this will give me a probability. It won't be the count. So all I'll have to do is scale that up by the number of variables. So I just multiply that. So then the claim, and if you want to, you can verify this, but it's almost so simple it's not that interesting. The sharp set of var5 is equal to 2 times is 2 to the number of variables of the semantics of the encoded program. Evaluated on true in the empty environment. Sorry, bad board work, but hopefully you could hear me, right? So that's a pretty easy reduction. So we just learned that computing the semantics is as hard as counting the number of solutions to a formula for this tiny language. Yeah?
This may be a naive question. Why do we care about complexity of evaluating denotational semantics? Because I thought that we only do operational semantics when we're implementing the language.
Beautiful question. Beautiful question. The question is, why do we care about the complexity of our denotational semantics? That's not what our computer will implement, right? Our computer is going to do something else. It'll run the program. And why do we care about the complexity of the denotational semantics? That's a really good question. And the answer to that question is that that's going to give us a lower bound on how good our operational semantics can be. So next lecture, we're going to talk about an operational semantics that will give us a way of computing this that isn't always exponential, right? Like the downside of these denotational semantics is that they're always exponential. You're just enumerating everything, right? Which isn't good. We hope to do better. We hope to give operational semantics that are better than just evaluating the denotational semantics. However, if I gave you an operational semantics that was faster, right? Somehow it was better than computing the denotational semantics. Well, then how can that square, right? My operational semantics are supposed to be adequate. Meaning, like, if I give you a denotation, then my operational semantics should be commensurate or compatible with that denotation. And I'll give you a definition for all this next time. But the problem is that if I can do a simple reduction from counting to computing denotation, how can I do an operational semantics that's faster than that? Does that make sense? So somehow this is telling us the worst case hardness, right? Our worst case hardness is going to somehow be bounded by this. Yeah.
Can you say again how does the encoding, how to turn the denotational semantics of the tiny people program into the solution of that set formula?
Yeah, sure. So how do I fill in a few more details of this?
Just rewrite that piece of
Yeah, I'll rewrite this one here.
that expression down to.
I will fix it up for you. So the claim is that sharp sat phi is equal to 2 to the number of variables in var5 times the semantics of the encoded program. I've only given you a sketch right now, right? You still have to show that this encoding is polytime and so on. I'm just kind of giving you the gist of the encoded program evaluated on the empty environment and the probability of true. Question? Yeah, you.
Yeah, I was wondering, maybe I'm skipping ahead too much. Do we end up having to do some kind of average case thing, or are we going to change like what we're using about complexity relative to?
Yeah, this is a great question. I've just shown you how hopeless we are, right? This language is somehow way too expressive, and how can we program in this thing when just evaluating its semantics is sharpie hard, right? And that to me is the fun, right? That to me is the fun. Because we have here, I showed you at the beginning of the lecture how much we want these things, right? We really want them. Like programming languages, people want them because they let us verify programs. AI people want them because they give us really cool and useful tools for reasoning about the world, solving all sorts of things. And I've just shown you why we can't have them, right? They're really hard to evaluate, really hard to compute. So what do we do? That's where the problem becomes really interesting to me. Because there's a very interesting language design space and a very interesting space of trying to find what kinds of programs we can handle, right? Obviously, this language is maybe too expressive, right? There's too many programs I can write, so I might need to make it less expressive in order to have programs that I know I can run. Or I need to come up with clever operational semantics, clever runtimes that aren't always worst case hard and maybe can handle certain kinds of programs, right? I need to walk this very fine line between the worst case hardness and the average case or practical hardness, right? And that's going to be what I'm hoping to show you guys in the next 2 lectures is 2 strategies for actually computing these semantics that isn't worst case hard on all cases. It'll still be worst case hard on some, right? The worst case hardness can't be avoided, but it'll find some interesting trade-off in this design space of languages we can actually run. Right? I think that's very interesting. Any other questions? Yeah.
You mentioned earlier that the claim that the complexity is proportional to an exponential number of variables is just like a conjecture. Is that not proven?
You're quizzing me on my knowledge of complexity. So to
More broadly, like, what's the difficulty here?
in what? In which? So in which?
Showing that it is the case, if it is the case.
Yeah. So how do we? So the question is, does exp time equal p space? That's what your question is. I believe that's open, but I'm not sure. I'm not a complexity theorist. There's lots of things that change very quickly in that field. Yeah.
How bad could it really be if we add product and function type?
Ah, lovely. Yeah, question is like, what's the price? So now you're asking a question that I really like. I'm going to write it on the board. I was just asked a really nice question. What's so bad about adding product types and sum types? And this is a question I want to add, which is,
Extend your omega.
it would, yeah, but it would be okay, right? So the question, I'm going to boil it down to, what's the price of my features? Right? What's the price of my features? Every time I add a new syntactic construct, notice I didn't have loops, didn't have lots of stuff, no functions, no first-class functions. Every time I add a new feature into this language, that's going to come at a price. And I've shown you the floor. Right? This language has nothing. And it's already really hard. And every time you add a new feature, you add loops, you add functions, etc., it's going to get worse. Right? So, you know, you might think, oh, well, it's hopeless. Right? How can we make interesting and practical languages when this worst case is so bad? And I think it's really cool that we can. There's actually a few really interesting and useful languages that are used today. And that's kind of what I wanted to conclude on before I let you guys go. Which is, if it's also hopeless and it's also hard, surely this must be abandoned. Right? How do we get around this? So there are some practical, widely used probabilistic programming languages that solve interesting problems. Right? So systems in the wild. And I would encourage you to go and look at them. There's some pretty cool ones, right? So I want to highlight one called Stan, which is widely used. Stan is a probabilistic programming language that was developed at Columbia. They teach a class in probability using this language, and it's been used in a lot of applications. It's been used in medicine. It's been used in computational biology. It's been used in population dynamics modeling. It's been used in a bunch of settings. And if you go to their webpage, you can look at case studies, and you'll see people making pretty cool programs in this programming language. It's a weird language, but it's kind of cool, right? So, you know, this worst case hardness is, of course, there, right? In fact, in their language, it's much worse because they have continuous random variables, so it becomes as hard as integrating, which is very bad, right? But it still works. They can still solve interesting problems in it, right? Stan does not have higher order functions. No, if you go look at Stan, you'll find it very interesting. It doesn't even really have control flow. Yeah, it's still useful, right? Then there's a few that were developed by Google and I almost said Facebook, Meta, excuse me. TensorFlow, probability. Is used within Google, I believe. It's still used. Haven't checked in on them in a while. There's some developed in Microsoft. Microsoft has a few. Can you repeat your question, please? This is a separate system developed by Google with similar design goals.
So TensorFlow probability is the name of the system.
It is. Yeah. There's one called Pyro, which is developed originally at Uber. So yeah, there's quite a few of these systems that people use in the wild, right? So they're finding interesting trade-offs in this design space for practical languages that solve interesting problems. So how are they doing that? Was there a question? Cool. Okay. Something I forgot to mention at the beginning of this class. I'll give you a little bit more context. On my webpage, you can find previous instances of probabilistic programming languages courses. And on those pages, I have like a collection of existing systems, notes, course notes, and things like that for you to go and kind of explore. I meant for this session to kind of be mostly an overview. So you should go and check out some of these languages. And like, if you wanted a fun kind of homework assignment to do before next lecture, here's what I would suggest. Check out the Tiny People, and also I would say, if you feel like it, Tiny Cond languages in the GitHub repo. Just look at them. And then go play with a language called WebPPL, which is a very nice, easy to use probabilistic programming language you can run online. And that's pretty fun. That can give you a taste of kind of what these things are about. So, right. Any other questions about kind of this high-level context here? Cool. So I was originally planning on talking about conditioning today, which is a very, very fun idea. And I will talk about it next time, but I'll preview it now. So oftentimes in probability, I mentioned earlier in one of the motivations within the AI context, this non-monotonicity, right? This idea that like I'm going to learn something about the world and update my beliefs about the world after I see it happen. And this happens all the time, right? Like for example, you know, if I'm trying to get a medical diagnosis, I could run a test, and the test would come back positive. Do I immediately conclude that I have the disease? If you've taken a COVID test and didn't get sick or whatever, I don't know, you might conclude that maybe that test was a false positive, right? And so when we want to do inference on situations such as this, where I observe the outcome of some probabilistic event, and I want to know the probability of some other event happening, that's conditioning. And we can add that into our language, and it will be a new operator, and it will be a new effect. It will look like this. Observe. E. E. And what it will do is it will say, from this point onward, assume that this thing happened, right? Assume the test came back positive or whatever. And this is going to be a really, really, really weird and interesting effect. I don't know of another one like it in programming languages. It reaches back in time and changes how things would have happened previously in the program. It's very non-local. It's very strange. It has very weird, if you like rewriting theory, it has very weird rewriting theory, right? This is a very, very, very fun syntactic construct. And it's really an interesting feature in a probabilistic programming language to have. So we're going to talk a little bit next time about this feature and also about how to actually implement probabilistic programming languages, how we avoid this worst case hardness, at least on some examples. Okay, cool. Any final questions? Yeah. Can you say your question again?
Oh, so there's just no way to use like something like functional type to encode.
So the question is, there's no way to use functions to encode observe or functional types? I'm not quite sure what you mean. Yeah. So is there no way to use functions to encode observe? That's a tricky question. If you have recursion, you can, sort of, depending on your semantic model of recursion. So yeah, it's one of these things, right, where it's like, you know, what is the price of the feature, right? Like if you wanted to get observed, could you get it with recursion, sort of, right? So we'll talk about that a little bit if we have time. If not, come find me. Happy to talk about that. Okay, wonderful. Oh, sorry, there was another question. Yeah.
I guess more general question. How does this kind of compare or contrast with like deep learning approaches?
Oh.
Learning from data. Where does this like complement?
Yeah, so the question is, like, in the context of AI, how does this compare or contrast with approaches like deep learning? I think it's a good question. So it's fundamentally a different learning model, right? So this is what you would call a Bayesian learning model if you wanted to learn parameters using observe, which I will maybe talk about. It starts to get, this starts to get a little bit hard to explain in the limited time that we have. But it is indeed possible to model learning of the style that you would see like in deep learning with probabilistic programming languages with observe, which is one of the reasons why observe is very interesting. It lets you model learning, right? You can update the parameters of your program after you see more data, which helps it kind of better approximate the world, right? It's a different model of learning. And if you like buzzwords, there's the frequentists and the Bayesians, and they hate each other, right? I don't know if you know about this. If you don't, there's a great paper from Leo Breman on frequentism, which I really like. Deep learning is frequentist, and this is Bayesian, if you wanted a way to separate it. And it's they have pros and cons. It's quite complicated. But I think that one of the real benefits of probabilistic programming languages from an AI perspective, and maybe I'll spend one more minute spewing propaganda, is that it's very interpretable. Right? I can look at my program, I can change it. I know exactly why it's making a decision it's making. If I want to, I can go in and change the syntax and get, bam, have a new model. That's really hard to do with deep learning. That's a big part of why the companies like it, actually. It solves a real problem of being able to interrogate, change your model. Should I stop? I'm 5 minutes over. Stop me when I need to be stopped, I guess. I don't know. I'll take one more question. How about that? Yeah. No, I didn't, but you can do it using case analysis, or you can, yeah. Okay. If you have more questions, I'll stick around, but I'll let you guys go. Thank you very much.